This is Math 151, and we're beginning Unit 2 in your textbook. That's actually Chapter 3, on the topic of derivatives. In Topic A, we'll explore the definition of the derivative, and this is actually going to build off of one of the exercises that you did in the very last classwork assignment, the applications of limits. The question that we're going to be investigating is, how do we find the slope of a tangent line to a curve? So eventually what I'd like to be able to do is find the slope of the line that just touches the curve at this point. That line right there, called the tangent line. Of course, the problem is, how do I find the slope of a line if I only know one point? Right? We know that in general, slope is y2 minus y1 over x2 minus x1. And at this point, I only have one point, an x1 and a y1, if you will. I don't have a second point that would allow me to actually calculate that slope. So what we were doing, and again, this should take you back to the problem from the classwork, is we were picking a second point, and instead of dealing with a tangent line, we were dealing with what was called a secant line. So just so that I can see what I'm doing, I'm going to pick my second point quite a ways away for this first one. Let's pick a second point on the line, and it's not going to be difficult to find a slope of the line between 2 points. We certainly know how to do that. So let's just sketch in this line, and then we'll start developing some notation. There's my secant line. And again, my goal right now is to find the slope of that secant line since I have 2 points. Here's some notation that we'll use for this. Let's go ahead and say that the original point, the one that eventually I want the tangent line, slope, I'm going to call that just the x value, just plain old x for right now. And then the x value down here, let's imagine that we've moved over a distance h along the x-axis. So this new x value is just x plus h. As far as the y values are concerned, if this graph is the graph y equals f of x, some generic function, then at this first point, the y value would just be f of x. And at the second point, I would have the y value f of x plus h. So, to calculate my slope, again I have y2 minus y1, so that would be f of x plus h minus f of x. Divided by x2 minus x1, x plus h minus x. Now, of course, in the denominator, I can get rid of those x's. X minus x is 0. I just have that h in the denominator. This expression right here, again, refers to the slope of the secant line. So I'm going to call it m for the secant line. And then we'll start imagining what would happen if I decreased the size of the h. So if I make my h value smaller, let's do a new x plus h, maybe here. So I got a littler h this time. My new point on the line is right oops, I'm sorry. My new point on the curve, rather, is right here. And so here's my new secant line. Okay. You'll notice that the first secant line had a slope quite a bit bigger than the tangent line. Now that I'm a little bit closer together in terms of my 2 points, the new secant line has a slope that's quite a bit closer to the actual slope of the tangent line. Now I could keep on doing this, right? I could make my points even closer together. Maybe I pick a point right about here. So this is the new x plus h for a much smaller h value yet. And now when I draw my secant line, I can see that we're even closer yet to the actual slope of the tangent line. It's going to be hard for me to draw them much closer together. You won't be able to see anymore. But as you can imagine, the smaller the h value gets, so in other words, in the limit, as the h value gets close to 0, the slope of the secant line will approach the slope of the tangent line. So as h approaches 0, the slope of the secant line will approach the slope of the tangent line. We can write that formally as a limit, and when we do, the slope of the tangent line is actually the derivative of the function. So we define the derivative of the function f of x as the limit as h goes to 0 of this function, f of x plus h minus f of x over h. Algebraically, that's the definition of the derivative. The notation we're going to give this, at least for now, is f prime of x. There are several other derivative notations that I'll introduce you to a little bit later on, but for right now we'll go with f prime of x. And geometrically, we'll always keep in mind that the derivative, which is just the value of this limit, is simply the slope of the tangent line to the graph of the function. If I want that slope at a specific point, where x equals a, then I can say that I'm finding f prime of a. And again, it represents the slope of the tangent line to the graph of f of x at the point where x equals a. All right. So what we're going to do next is we're going to take a look at a problem graphically. We're going to use the graph to numerically estimate some tangent line slopes or derivatives. And then we'll actually follow up by calculating those slopes using the algebraic or analytic formula that we developed. So again, we're going to look at this next problem graphically, and then numerically, and then finally analytically. What I have here is probably a graph that you recognize. It's simply the graph of f of x equals x squared. And we're going to try and estimate f prime of a for each of the values in the table by simply thinking about the tangent line slopes, which we'll estimate by sketching on the graph. Right. So let's see here. The first point that we're asked to look at is an a value of 0.5. So f prime of 0.5 is going to be the slope of the tangent line at 0.5. And I'm going to go over here to x equals about 0.5. And there's the point on the graph. I'm just going to kind of try and line up my ruler so that it looks like I'm drawing a line that's pretty close to tangent, just touching the curve at that point, but not really cutting through it. As I look at that line, I'm going to notice that to go from, say, this point to this point, looks like I've pretty much gone over 1 and up about 1, doesn't it? So I think my slope is 1 over 1, or 1. And so I'm going to say I think that's the derivative at a equals 0.5. Let's keep going. Let's go to a equal 1. 1 would be right here, so our point in the graph is there. And again, this is just an estimate now, but I'm going to try to grab my ruler and estimate about how that would look if the line was just going to touch the curve at that point. It's almost like balancing the line on the curve. If I look at the slope of this pink line that I just drew, here's one point right here at 1, 1, and it looks like it kind of goes through another point up here. So that's up 2 and over 1. And so I'm thinking my slope, which is my derivative for the tangent line, is just 2. All right, how about at x equals 2, which is the next point in our table here? Be right there. And again, same deal. It's kind of getting steeper now, so I'm going to estimate about what the tangent line would look like here. Maybe about like that. Again, just touching the curve. Try not to cut through in more than one point. And for this line, got another point up here. Looks like we've gone up, my line's not quite 4, but pretty close to 4 and over 1. So the slope of that tangent line looks like about 4, meaning I'm going to say the derivative is about 4. And then I'm going to draw one more, and then we're going to use a little geometry to estimate the rest. At x equals 0, that's the vertex of the parabola. And our tangent line there is just going to be the x-axis, right? It's going to be perfectly horizontal. Right there. So the slope is 0. All right. The rest of these values are just the negatives, the opposites of the x values we already have. And if you imagine with me for a moment, here at negative 0.5, if I were to draw the tangent line, by the symmetry, the slope would just be the exact opposite of what I had at positive 0.5, right? It'll have a negative slope, but I'm just going to use the value I already had here and say I think that would make that negative 1. And similarly, at negative 1, by the symmetry, it would just be the exact opposite of the slope at positive 1. So we'll go with negative 2. And at 2 and negative 2, again, my slopes would be opposite, so I'm going to go with negative 4 there. All right, so graphically, and then a table of values numerically, we've estimated the slopes at a few points, or in other words, the derivative at a few different x values for the function f of x equals x squared. I'm now going to go ahead and say, all right, we developed an analytic formula for the derivative. It was the limit, right, of that, what we used to call the difference quotient. We still can. And I'm now going to do the same problem analytically using what we call the definition of the derivative. So any time you see use the definition of the derivative, that means they want you to find the derivative analytically, or in other words, algebraically. And they specifically want us to use the formula we developed, which was f prime of x, was the limit as h goes to 0 of f of x plus h minus f of x divided by h, right? And again, just a reminder, that came from the slope of the secant line when I brought the 2 points really close together, letting h go to 0. All right, so let's do this. F of x plus h. If I plug x plus h into my function, I'm going to get x plus h squared minus f of x itself, which was just x squared, divided by h. And notice in terms of the limits that you're used to seeing, if h is 0, the top would be x squared minus x squared, which would be 0. And h on the bottom is also 0. So this is one of those indeterminate forms that we've seen a whole bunch of times in the last unit. In order to try and find the actual limit here, we're going to go ahead and do some algebra. And in this case, I'm going to square out that x plus h and see what happens. Squaring that would give me x squared plus, don't forget that middle term, 2xh, right? xh and another xh for the outers, so 2xh plus h squared. And then I still have this minus x squared over h. And now some good things are going to start to happen. Right? The x squareds go away, they add up to 0, x squared minus x squared. And on the top, I could factor out an h, which gives me 2x plus h. And this was really the key. This allows me to divide out that problem spot. I'm going to get rid of the h in the denominator, which is going to get rid of the 0 in the denominator by dividing out my h's right here. And I now have 2x plus the h, which is 0, or just 2x. So we say that the derivative of the function f of x equals x squared is 2x. And I can now use that formula to fill in the slopes, the f primes, the derivatives, for all of the a values. So if f prime of x is 2x, then f prime of a is going to be 2a. And literally I'm going to double all of these to get my slopes or my derivatives. So doubling would give me 1, 2, 4. Doubling 0 is still 0. And then -1, -2, and -4. Okay. Now, of course, I kind of knew where I was going, so I guided us a little bit as I drew, but hopefully you agree that our drawings were reasonable. And notice that those values that I've gotten from the formula now are the exact same slopes that we predicted by looking at the graph. All right, we're going to do one more problem based on this particular function before we look at another one. I would like to actually find the equation of the tangent line for f of x equals x squared, specifically at the point where x equals 2. Now remember, to find the equation of a line, you need to know two things, right? You need to know a slope and a point. So what we'll typically do for tangent lines is we'll say to get the slope of the tangent line, we'll always just use the derivative. And in this case, since it was x equals 2, I can actually grab that right off of here. We already have it. It's 4, specifically for x equals 2. Point that you're going to find the way you've always found points, right? If we know that x is 2, then we can get the y value just by plugging that back into the original function. So 2 squared would give us 4. And our point is 2, 4. And then again, at this point, you can use whatever your favorite method for finding the equation of a line is. I tend to like y equals mx plus b, but point slope form's fine too if you prefer that. I've got a y value of 4, a slope of 4, and an x value of 2. So it looks like I'm going to get negative 4 for a b value. So now I know m and b, and the equation of my tangent line is y equals 4x minus 4. All right. Just a comment. It's a little hard to see because I don't have quite enough space on the graph, but you'll notice here the blue line here is actually the tangent line at x equal 2. And that was the one we did find a slope of pretty close to 4. And the y-intercept is cut off, but what this is telling me is if I kept on going back down until I got to the y-intercept, it would have been down here at negative 4. And that certainly seems reasonable based on the picture that we drew. All right, we are going to stop here for this one, and we'll continue in the next part of section A to do some more examples of finding derivatives using this definition.